This problem is an exercise in all the things you can pull out of a velocity time graph. So there are 5 parts. Part E doesn't fit on this screen, but given the velocity versus time graph to the left, what is the initial velocity of the particle? What is the displacement of the particle? What is the average acceleration of the particle over the first 20 seconds? What is the instantaneous acceleration of the particle at 45 seconds? And we assume when they say what is the, for these two, that the displacement, they mean during the entire motion. Because it doesn't say explicitly, but we'll figure it out. All right. Part A, what is the initial velocity of the particle? So initial. Here we mean, kind of logically enough, the t equals 0 value. So we just go over to the graph and we say when t equals 0, now remember this is the t-axis, so we look for the 0 on the t-axis and we find the velocity, and perhaps not shockingly, we pretty easily read this as that the velocity at the start is 0.5 meters per second. Part B, what is the displacement delta x of the particle? And again, we'll say over the entire 50 seconds. So we want to sort of remind ourselves on a VT graph, delta x is the area trapped. In this case, we have 3 distinct regions that will be easiest to get the measure of. Our first region is, this one. And I'll call, all right, our second region is this one. And our third region is this one. Region 1 is a little annoying in that it sort of has 2 parts to it, which I'll call A11 and A12. Or you could do trapezoid rule, but I always just forget the trapezoid rule. So A12 is the area of this triangle. It's a right triangle, so it's a half times the base, which is 20 seconds, times the height, which is 1.5 seconds. So we get 15 meters, and then that was A11, and A12 is the rectangle. That's easier. It has a base of 20 seconds and a height of half a meter per second, and so we get 10 more meters. For the other region here, A2, that's just a rectangle, so that's easy. That's a base of 20 seconds and a height of 2 meters per second, so that's 40. And then here we have a right triangle for A3, which is 1/2 times a base of 10 seconds times the height of 2 meters per second. That's 10 meters. And we go back here and say, well, the actual delta x is just all those areas. Which I guess comes out to be 15 meters plus 10 meters plus 40 meters plus 10 meters, which is 75 meters. Part C, what is the average acceleration of the particle over the first 20 seconds? So we come with that the average acceleration is delta v over delta t for the interval we're talking about. And then we should pick some points that we'll measure between. So let's say we'll take as our first point here and as our second point here. So we have 2 meters per second and 20 seconds at the end, and we have 0.5 meters per second at 0 seconds. And we come back here and say, well, that's 1.5 meters per second over 20 seconds. which is 0.075, and meters per second is meters per second squared. Part D, what is the instantaneous acceleration A of the particle at 45 seconds? And what we want for this is to remember that the actual instantaneous acceleration, we can write some awful mathematics on it, which I will write here, but don't worry about. But this is the slope of the tangent of the VT curve. In this particular case, our curve is really a line, so the slope will be easy. What point are they talking about? Well, 45 seconds. They're talking about the slope of the line containing that point. So the acceleration is going to be some difference, as always, between two different points. But I can pick any points on the line, so I'm going to pick that as my initial point, which is 40 seconds and 2 meters per second. And then I'm going to pick over here as my final point, and that is 50 seconds and 0 meters per second. Why did I pick those? Because they're really easy to read. All right, I would have done just as well if I had taken the blue dot. In fact, I think I'll show that when we're all done here. So what do we get here? We get minus 2 meters per second over 10 meters per second squared, or minus 0.2 meters per second square. How about if we had done an alternate, and I use the blue point? So then I have A equals this stuff, and our initial point would still be 2 meters per second and 40 seconds, but now our final point would have been 1 meter per second and 45 seconds. And then I get minus 1 meter per second over 5 meters per second, over 5 seconds, which is also, of course, minus 0.2. It doesn't really matter what points we take because we're taking the slope of a line. This question's a little awkward because it looks a lot like C, but remember that C was saying what is your average over this entire interval, and so we would just take the starting endpoints, and D is asking your acceleration at this point, but notice that during this interval the acceleration is constant, so it's the same as if we had taken the average, because one way of defining a thing which is constant is that it's always equal to its average. All right, and then they ask which of the graphs below is the correct acceleration versus time plot for the motion described in the previous part. And I guess they have the values in there that you could actually read, but I want to walk through it as to how we would figure out. And it's usually for multiple choice. It's as easy to eliminate the bad choices as to get the right choice. So let's see if we can. Well, our first thing we see right away is there's a region where the graph is flat. And when the graph is flat, its slope is 0, and the acceleration is the slope. So I need a region where there's an acceleration of 0 in the middle, and we can see right away that A is out. It doesn't have that. On the other hand, B, C, and D do have it. Next, we know that the acceleration at the start is the slope of this line, and it should be positive. So we can eliminate graph D, because it starts off with an acceleration that's negative. So now we're down to either B or C. And then we say over here we have a graph which is an acceleration which is negative. That doesn't help. They both have accelerations negative. But this is a line, and the slope of a line is constant. Whereas over here the acceleration is not constant. It starts at 0 and grows to over some finite interval to minus 0.2. And so C is also out. So our only possible choice is B. If we confirm it, yep, we have some acceleration at the start. It drops to 0. And then because this line is steeper than this line, this value should have a greater magnitude than that value. And we see that that's actually true. So it's B.